Now, in this video, we are going to discuss about the shear stress and shear strain. So here, first we're going to consider the shear stress. So there are two figures here. One plate, there are two plates, one fixed over the other, and it is riveted at this point. And when you are considering the section at this, and when you apply the two parallel, equal and opposite forces, which is acting on the two different plates, then what happens? Then there will going to be a sheared on the pin, which is at this point. So it will take out this onto the left hand side. So which is as shown in the figure B. So when a body or a section is subjected to two equal and opposite forces, so the one P is acting on this side and the other one is acting on this side, acting parallel or tangential across resisting section, that is figure A, and tends to shear off the body across the section as shown in the figure B. So that is at this point. Then the force is called shear force, and the stress induced is nothing but shear stress, and the corresponding strain is known as the shear strain. So now we're going to consider a block of the element ABCD, wherein you have the one end of the bar, which one end of the rectangular bar, which is AB, is fixed, and then you apply a shear force P at the top surface. So consider the section XX and applied force as shown in the figure A. The lower part will be in equilibrium if resisting force P dash is equal to the applied force as shown in the figure B. So in order to keep this body in equilibrium when the shear force is applied, so you're going to have the equal and opposite force here, so that the body will going to be, or the member or the bar will going to be in equilibrium condition. But when you are considering the section, what happens? Naturally, the lower part will not be in equilibrium. So because there is a change because the force is applied in this direction, but here we don't have any force because we have considered the section. So in order to keep this body in the equilibrium condition, so since the shear force is acting, shear load is acting on this, shear force is acting on this direction. So then in order to keep this body in equilibrium, so there should be a resisting force whose magnitude is equal to the same as this. We're going to consider that as P dash, and it acts in the opposite direction to that. So therefore, the resisting force P dash will be equal to the applied force, which is P as shown in figure B. Similarly, if you are considering the section on the top surface, since the upper part will be in equilibrium, if resisting force P dash is equal to the applied force P, and is shown in figure C. This resistance, which is known as the shear resistance, and the shear resistance per unit area is known as shear stress, tau. It is denoted by tau. That P is the applied tangential force and P dash is the shear resistance. Then A is the shear area. So what is the shear stress? So shear resistance by shear area. Shear resistance is nothing but applied tangential force by shear area. So what is applied tangential force, which is P by A? So because P dash is equal to P, so you're going to get it as P by A. So what is shear stress? So when you are considering the shear stress here, so again we are considering the rectangular bar of ABCD, wherein the top surface is applied with the shear force P, and in the bottom surface will going to have the equal in magnitude but in opposite direction to keep the body in equilibrium condition, wherein AB will going to be the length, which will going to be L, and AD is the one which will going to be the height. So once you apply this, so in the top surface, that C will going to be displaced to C1 and D will going to be displaced to D1, wherein the displacement what you get from C to C1 will be delta L. Similarly, from D to D1 will going to be the delta L. And phi is the shear angle, phi. Now we will take the rectangular block of height h and L, unit width is subjected to shear force P on the top and bottom faces. As the bottom face is fixed, the block will going to be deformed to the position AB C1 D1 due to the applied shear force P as shown in the figure B. So let the transverse or horizontal displacement at the upper face is delta L, height of the block be h, and the shear strain be phi. So what is shear strain? Shear strain is the transverse displacement by the distance between upper and lower faces. So what is the transfer displacement, which is dt1 by ed? What is dt1, which is going to be delta L by h? So shear strain will be phi, which will be equal to delta L by h. So since shear strain is the angle what you are going to get, so opposite to that angle is the opposite side, which is going to be delta L, and h is the adjacent side. So therefore you can say that tan phi is equal to delta L by h. Since phi is small, tan phi is equal to phi. Therefore shear strain phi will be equal to delta L by h. So this is how we will be able to explain about the shear stress and shear strain. Thank you.